for the introduction, and thanks for the invitation and giving me the opportunity to introduce variational discretization frameworks for geophysical flow models. I'm sorry, yes. For geophysical flow models, this is joint work with François Gay-Balmaz. I structured the talk in the following way. First, I will introduce the problem, what we deal with in geophysical fluid dynamics. I also discuss what kind of models we discuss about. Part 2, we are going to introduce the variational discretization framework for geophysical fluid dynamics. In part 3, I present some numerical results, and then I come to some conclusions and go to the outlook. Okay. What problems do we study in geophysical fluid dynamics? So here we are interested in the studying of atmospheric and oceanic flow on a rotating Earth. So we have different challenges here. So this is a multi-scale phenomena. So we're dealing with scales of meters. So when we want to resolve clouds, for instance, up to thousands of kilometers. So large-scale flows that stretch all over the Earth. So we have integrations time that span from hours in weather forecast up to thousands of years in long-term climate simulations. So we have a spherical geometry, so that means we don't have regular meshes, so our discretizations have to cope with unstructured, non-regular meshes, like shown here. Our icosahedral meshes often used in the situations. And we need numerical algorithms that are efficient, so we have this long integration times with a lot of degrees of freedom, a lot of processes, and we want to have accurate and consistent discretizations. The acronym for this one is a structure-preserving discretization. So what is a structure-preserving discretization and why do we need it? This is discussed here. So when we talk about a structure-preserving discretization, we have discretizations that share important structure of the continuous equation. For instance, invariance, so we want that energy, mass, vorticity, and entropy, or the circulation theorem in general, is conserved. On the discrete level, we also want that in the discrete level, geometrical properties like this vector identities or the Helmholtz decomposition of velocity is also preserved. Or that flows stay balanced, because on the atmosphere we know we have a hydrostatic balance, so we know that more dense particles are below lighter particles. So this balance has to stay in our numerical model, otherwise it doesn't make sense. So, and why is this important? This is important because when we don't have structure preserving, we have a wrong interaction between energy and entropy on the scales that leads to a wrong representation of waves. And on the other hand, we need also structure preservation because this is important to have good statistical means. It can be shown that if we use not structure preserving schemes, that the statistical means can be wrong. So this is why it is important, and here variational methods come into account because they are very promising in developing these structure-preserving methods. And what we see later is we can also come to some efficient methods, not finite element methods, but mass matrix free elements. So they are more efficient than standard finite element approaches. So we hope so. Okay. The models I'm going to discuss about here are soundproof models and compressible models. So let me explain soundproof models. They are called soundproof because we filter out gravity waves. So they are supposed not to be important in atmospheric modeling. So we filter them out. And here we have the momentum equation. And in this momentum equation, we have two terms. We have a buoyancy term that takes care of when we put a particle out of its equilibrium state, and the gravitation term. These two terms are in balance, and what you see here on the slice model of the atmosphere, here you see that there's wave evolving in time, and these are by a balance of these two terms. And we can switch between different approximations. They are called Boussinesque, anelastic, and pseudo-incompressible models by modifying these terms. So I go to this, for instance, the pseudo-incompressible model. Here we have a nonlinear term, and in the Boussinesque model, this term is much more simplified. And we change here the incompressibility condition by either having here a density, a background density. When I talk about a quantity that has bar, I mean a background density that only depends on the height field. So we see that here we can approximate these models by background stratification and some quantities that also depend on time. It's not so important to understand the entire equation set. I just want to introduce you what kind of model we discuss and how we discretize them by variational principles. On the other hand, we also consider the compressible rotating shallow water equations. Here we have these large-scale flows where geostrophic balance is important. So we have the Coriolis term that takes into account the Earth rotation and the particles feel a force by this Coriolis force, and this Coriolis force is balanced by a gravitational force, such that this large-scale lows and highs in the atmosphere can exist. And this is important that this can be well modeled. So these two models are standard models that are used in the development, in the first step of a development of a global climate model or global numerical weather prediction model. And this is why they are of interest, because they share a lot of important features that we need later on. They are, in the end, we want to have full 3D models, but to develop the variational finite element, the variational discretization framework here, these are good starting points. So now let me introduce the variational discretization framework, and we want to cast these two models that I just introduced in this variational framework. So a short recall on what we mean with variational principles. Let's start with a Hamiltonian principle. We have a Lagrangian and we search for the extremum of this curve. When we describe fluids, we describe the fluid by diffeomorphism groups on the fluid domain M. And now we have the possibility to cast into this variational framework this soundproof and the compressible model that I just introduced. For the soundproof model, we introduce diffeomorphisms that preserve a weighted volume form, and by switching these three parameters here, we can switch between three different soundproof models. And in the compressible case, we just allow all diffeomorphisms on this manifold, in this group. Now, to describe a fluid, we want to reduce the problem, so we do a reduction step to, here we have a Lagrangian picture, so we have a material representation. Here we want to go to a spatial representation, because this reduces the problem tremendously. And so we come to a spatial Lagrangian, where now the Lagrangian doesn't depend on the group, on the diffeomorphisms itself, but on spatial or on Eulerian velocity field u, and in the soundproof case on a potential temperature. This was this profile that I showed here. It's a background stratification of the field, or in the compressible fluid, it depends simply on the fluid depth of a shallow water column. So now to introduce the discretization framework, let me first present you an overview. I will first present some details on this one, and I will show you how that the discretization framework mimics step by step the continuous world. We just translate step by step this continuous variational principle into the discrete world by introducing suitable discretizations and by suitable approximations. So here, let's first concentrate on the right-hand side, on the left-hand side. Here, to formulate the variational principle, we start with the diffeomorphism group. This group induces action on functions that is defined like that. So it acts from the left by composition on functions. Densities have to be treated differently, but densities we only need for the compressible case. So now when we do the reduction process, when we want to describe spatial velocity fields and spatial fields for height field or for the potential temperature field, we take this is valid for both cases, and for the soundproof model, we have this relation which comes from the group action on functions, and for the compressible case, we have this action which comes from the group action on densities. And in the end, we can formulate the Euler-Poincaré principle like that. We have a spatial Lagrangian, we have constraint variations. This is valid for both cases, and now we have constraint variations that differ. For the soundproof models, it looks like that. For the compressible model, it looks like that. And now, as I said before, the discretization is now, we mimic step by step this theory into a discrete world. And let's do this now step by step. So, okay, we start with a discrete diffeomorphism group. Okay, we start with a compressible case, and here we define the diffeomorphisms are groups of a general linear matrices with positive determinant. And under this condition, and what does this condition mean? So we have here constant function, and discrete functions are when we have a mesh, we sample at every mesh point, the cell center, we sample this, the value, and this gives us a discrete function. So to every cell point, there is a degree of freedom associated. This will give us a degree of freedom. And now this matrix acts with matrix multiplication on this function, and we want to allow only groups, matrices that fulfill this, and this means that constant functions are mapped to constant functions. So this is a requirement that is logic. And in the soundproof case, we need an additional constraint. Instead of, for this one, we need also a constraint that the weighted volume forms are preserved. What does it mean? So it means we have an incompressible flow, or we have a weighted incompressible flow. So by these two definitions, we have now modeled the continuous diffeomorphism groups by discrete matrix groups. So this is the first step, and it's important now to define the action. As I said, we want to see how the action works on discrete functions, and we define it by matrix multiplication, and we define the action on discrete functions such that this diagram commutes. So either I apply a continuous group element on F, and I come to this formulation, and then I discretize, and I come to this formulation, or at first I discretize, and then I apply the discrete group element, and this diagram must commute. So now we have the groups, and we have the discrete functions. Now let us go to the Lie algebra. So by taking the derivative of the continuous and the discontinuous action on the identity, we are able to identify that that a matrix A that acts on F is in fact minus the directional derivative. So we see this by these definitions, and this allows us to derive Lie algebras associated to the Lie groups from above. So we have now a Lie algebra such that when elements of R act on the constant, it's 0. And here, in the case of the soundproof model, we have also this constraint, but we have an additional constraint which comes from the incompressibility constraint. But it's now translated to the Lie algebra level. But here we have to be careful, because this definition doesn't give us now real discrete vector fields. We need additional constraints that we have to take into account in the variational principle to really describe derivatives. Discrete vector fields. Sorry. So then, how do these non-holonomic constraints look like? For the compressible and for the soundproof cases, this is now also, it seems natural that we don't want to allow fluxes over grid boxes that are not over neighbors. So if there's more than one neighbor away, these fluxes should be 0. So this is included in this constraint here. So if n is not a adjusted cell, then this matrix elements should be 0. And an additional constraint we need for the compressible case, here we need that the matrix elements multiplied by the volume fulfill this antisymmetry relation. And then we have another constraint. So if you don't understand all the details, it's clear it's a little bit technical. I just wanted to say that these non-holonomic constraints have to be taken into account in the Euler-Poincaré-D'Alembert principle to find suitable approximations of the continuous vector fields. And this is in fact what we could show here. When we take these non-holonomic constraints into account, the matrix A that we find and that the elements are shown here are in fact converged versus a continuous vector field. So we could show this in a recent paper together with François. And how does these elements also have a physical meaning. So when we look at the fluxes over cells, when we look at cells elements, IAJ is in fact a flux over a cell. So when we look here, this describes a normal flux over this cell with a normal vector n, and we have an integral over the domain D, and this is in fact a flux over this cell boundary. And in a compressible case, we have also a term in the diagonal of the matrix A, and this diagonal is in fact the divergence associated to each cell. And in the soundproof model, this is a little bit different. We only have the fluxes over the cells, and when we sum up these things all over the cells, we come to 0, and this encodes the incompressibility condition. So here we have a compressible flow. This is why we have this compressible, this divergence part here on the diagonal of the A matrix. Here we don't have it because we have incompressible flow. Okay. So, and then let's go further. So we also want to have how discrete advected quantities are advected by the elements. So here, just mention it shortly, the discrete fluid densities are defined as a dual action with respect to action on discrete functions. So this dual action is defined via LA2 pairing in this way. For the soundproof models, because discrete potential temperature is a function, it's simply defined like a function. So, and then we know how we can update it in time. So everything is now prepared for formulating the Euler-Poincaré-D'Alembert principle. Now, for a variation of a discrete Lagrangian with discrete matrix elements and discrete advected quantities, we have constraint variations also written in a discrete sense. Here we distinguish again between a compressible and the soundproof model. I don't go into detail here, but what we find is now Euler-Poincaré equations that allow us to discretize by choosing like discrete Lagrangian, just putting it here inside, we will immediately find the discretization. So here we have a projection operator in this case. This projection operator takes into account the non-holonomic constraints, and we have a continuity equation, here a discrete one. In the soundproof case, we have here this formulation. It looks similar to that. Here we have the discrete Lie brackets that take into account the non-linearities of this flow. And here we have a discrete pressure that is not here, because here we have this projection operator. Here there comes a discrete pressure into account. So what is the guts? What is the important part of this? We have now general formulations that allow us to discretize by formulating the Lagrangian without any ambiguity, the discrete set of equations. Let me show this on this example. I start with a discrete Lagrangian. We have formulated the velocities and d in this form. This is an approximation of the continuous equation like that. You see, here we have the kinetic energy term, here we have the rotation term, here we have the potential energy term. We need discrete pairings. We can define them uniquely, and then we can calculate the discrete functional derivatives. We put these functional derivatives here inside, and we come to a set of equations. So it looks complicated. I just wanted to say that this is the nonlinear part, this is the kinetic energy term, this is the gravitational term, and this is the continuity equation. So this scheme differs from known finite difference-like schemes. So, and we are very happy that it worked so well and that it went through so well. And I cannot go into detail of these things. If you're interested, look in the proceedings. I just show you some numerical examples. I skipped the time integration part. So here we show that for the rotating shallow water case, we conserve energy on a flat, so on an approximation of the sphere by a flat F-plane. We have very nice energy conservation. On the sphere we have a slight drift, but we know where the problems are, so we are working on having a fully variational integrators on that. We conserve steady state solutions, mass and potential vorticity are preserved at machine precision. So these are all quantities that are very, very important for large scale geophysical flow models. And the soundproof models show a similar behavior. Here we have convergence. Here we show the convergence for an F-plane model. Here we show the convergence on the sphere. So these are the solutions, steady state solutions that converge versus the analytic solutions. So not only the theory converges, but also the solution converges. So this is so nice, and also the error in the energy converges in first order. So this agrees that our time integrator is in fact a variational time integrator. So, okay, and we close with some eye candy. So here for the soundproof model, we have a bubble, a warm bubble in a cold air. So it rises up, and here I compare regular and irregular meshes. You see that the variational integrator is also capable to take irregularity into account. I skip this one. And finally, the rotating shallow water. Here we have a large-scale flow. Here we have a mountain, and after 14 days, this large-scale flow pattern forms, and this agrees well with literature. And we also see that this large-scale Rossby waves transport our weather pattern over the globe. And this is also very well preserved, and this also agrees very well with the literature. And with this, I come to the conclusion. So we developed this variation discretization framework. This is very good for GFD models because it has good conservation properties. It's applicable to a wide range of fields. And in future, we go to full 3D compressible fluids. We develop higher order schemes, and we also want to introduce and include stochastic processes. Thank you.